All right, so I'll be talking about this recent paper with Edward Witten, and it's also, as Hong mentioned, it'll be related to the last talk, so I'll try to use some of the same language. So the ADS-CFT correspondence has led to tremendous progress in understanding quantum gravity in open spacetimes, namely asymptotically anti-de Sitter spacetimes. And it would be really nice if we could take what we've learned from there and understand quantum gravity in closed universes within the same framework of ADS-CFT. So using just standard wormhole analysis, we've talked about wormholes a lot already during this conference. I'll show that there's some obstruction to realizing closed universes within the standard framework of ADS-CFT. And I'll close with some more speculative ideas for how we could maybe recover the baby universe within some modified version of ADS-CFT that could include closed universes. So first, I'll talk about a closed universe puzzle that's been referenced already. And I'll take a bit of an aside into how operators and states behave in the thermodynamic limit, or in the case of ADS-CFT, the large N limit, and discuss how you can have emergent mixed states in this thermodynamic limit, both for normal many-body systems and for black holes. And rephrasing in this language, it'll be clear how this resolves the puzzle I'll set up earlier in this closed universe puzzle. And finally, I'll end with some more fun speculations. Okay, so the ADS-CFT dictionary asserts that the bulk partition function is equal to a boundary partition function. So the full bulk quantum gravity path integral is equal to some CFT path integral. So in the bulk, we have G Newton, and this is inversely related to n, or the number of local degrees of freedom in our theory. So the large N limit of the ADS-CFT corresponds to the semiclassical limit of the bulk, and this is where the correspondence is best understood. So a canonical example is if we take a thermal partition function in the boundary theory. This is computed by some Euclidean path integral on some manifold I've chosen to be a sphere times an S1, which is the thermal circle. And for sufficiently large beta, the dominant saddle is some thermal gas of particles in ADS. And this has an entropy that's order n to the 0, so some order 1 entropy. But for sufficiently small beta, the dominant saddle in the bulk is given by an ADS Schwarzschild black hole that has order n squared entropy. So thermal states can always be purified. Actually, all states can always be purified. And it will be purified on 2 copies of the CFT via the thermal field double. So here I've written the state, the thermal field double, as an operator. So we have an operator on one side. On one Hilbert space can be interpreted as a state on 2 sides of the Hilbert space. And this is the usual way of expanding in energy eigenstates of the left and right CFT. And so again, depending on beta, this is either dual to 2 ADS spacetimes, each look thermal and they're entangled with each other in this way, or at sufficiently high temperatures, this is dual to a 2-sided black hole, where this is the right exterior and this is the left exterior. So there's an interesting generalization of the thermal field double state called these partially entangled thermal states, I'll say PETs. And these come from modifying this thermal field double state by inserting some operator O. I won't be so specific about what this operator is, but now this comes with some normalization. In the case where O was the identity operator, this is just the usual thermal field double state. And so this is similarly a pure state on 2 copies of the CFT. It's important that this O has some large energy so that it's going to back react on the spacetime. So we again have 2 phases, and for small beta, there's a bulk gravity solution with some matter shell. For small beta, there's a bulk gravity solution dual to this, which is this long wormhole. This matter shell is supporting this long wormhole, and we still have ADS Schwarzschild in the exteriors. But for large beta, the dual geometry has 2 ADS regions and a disconnected closed universe supported by this matter shell. And this is in some non-trivial tripartite entangled state. And so it appears that ADS-CFT can describe quantum gravity of closed universes using states like this, for example. And in particular, in Lorentz signature, this has some Big Bang, Big Crunch singularity. So this sounds great. So I'll quickly review a puzzle by Antonini and Rath that I think is a reformulation of this factorization puzzle, but in a really nice way that lets us actually go and figure out what's going on. So in the large beta regime, we're going to focus on where you have this baby universe. This PET state can be expanded as an entangled state of finite energy excitations above the vacuum. And so here, these are just finite energy excitations and some coefficients,Cij's. And so this is standard ADS-CFT. We understand what finite excitations are above the vacuum, and they're dual to finite excitations of the vacuum ADS. And so this appears to be dual to an entangled state of two ADS spaces without a closed universe. And so what the contradiction that they raised is that this state can't be dual to both two ADS spaces in a bipartite entangled state, and at the same time be dual to two ADS spacetimes that are themselves entangled with this baby universe. Those two ADS spacetimes that are entangled into the baby universe is a mixed state by itself because of this entanglement. And so this was a puzzle, and we're going to resolve this puzzle by showing that states in ADS-CFT with baby universes, at least prepared by Euclidean path integral, cannot have large n limits. And so this is going to resolve this puzzle. And in particular, in this decomposition, theCij's aren't going to be able to converge in the large n limit. So let's just consider a more simple example of n qubits. And the Hilbert space of n qubits is just C2 to the n. And if we consider just some finite number, the algebra of operators that act on this Hilbert space can be just generated by usual Pauli string operators. This Hilbert space of n qubits doesn't have a good thermodynamic limit in itself. This is way too big of a Hilbert space. And instead, what we do is we have to choose some sort of reference state, some sort of vacuum, and consider a Hilbert space built up as finite excitations above this vacuum and complete it appropriately. And regardless how we do this, there's always a good algebra that comes from in the thermodynamic limit. And this is the algebra that's generated by finite Pauli string operators, sometimes called UHF algebra. And this can be completed in different ways depending on what sequence of states, what reference state we consider. So in this sense, not all operators or states are going to survive the large n limit. We have to consider some subset. And losing some of these operators and states in the large n limit is some sort of information loss that we can make more precise. So when we take the thermodynamic limit, we're always going to be considering a sequence of states for every value of n. So any number of qubits n, we take some state psi. In familiar settings, this sequence is going to converge to a pure state. So if we just considered a sequence of vectors that are all spin up on the first n qubits, and then we just have some reference vector on the rest, this sequence of states is going to converge to a pure state. It's also very easy to come up with examples where sequences of states aren't going to converge. For example, meaning that that the expectation values of all operators converge to some number. And so, for example, if we took for all even n, we take all spin up on the first n qubits, and for all odd n, we take all spin down on the first n qubits. This is, of course, oscillating back and forth, and we're not going to have a convergent sequence of states. And maybe the most interesting option is that you can have a sequence of pure states, these psi n's, that for every finite value of n, the vector is pure. But when you take the large n limit, you get a mixed state. And so recall a mixed state is described by some incoherent some classical mixture of pure states. So here I've taken the outer product of some pure states, and you have at least two of these pi's are greater than 0. So let's consider a very simple example of where this can happen. So let's consider psi n, where for each vector, for each n, we take a cat state on the first n qubits. So an equal superposition of all up and all down. And yeah, with this reference state. And so this is a manifestly pure state for any finite value of n. It's just some vector. Now we can take any operator A that's in this algebra, that's just finite Pauli spins generated by that. And let's say that it has support on k qubits. K is some fixed number. So as we take n larger, n is eventually going to become larger than k. And the expectation value of any sort of operator that we had chosen initially is going to decohere. So the expectation value is going to just be an equal a classical mixture of the expectation value in the all up state and the all down state. And so this is a mixed state. This is a classical mixture of two pure states. And so we see that this sequence of pure states in the thermodynamic limit becomes a mixed state. And so this particular mixed state has some entropy log 2. We have some information loss. And this is true even though all of these had 0 entropy. All of the psi n's had finite n. So more generally, there's the eigenstate thermalization hypothesis, which asserts that high energy states in quantum chaotic systems, for a suitable class of simple operators, they behave like this. So if we take some sequence of states, we have EI is some high energy eigenstate of energy E. The expectation values of some operator are some smooth function, which is this FO of E. So it depends on both the operator and the energy, plus some erratic part right here, which this is some gamma is some pseudo-random variable, and it's exponentially suppressed in the microcanonical entropy. So the thermodynamic in the thermodynamic limit, the microcanonical entropy diverges, and so these sequence of states really do converge to a state in the large n limit. So this term just goes away completely, and we're going to just converge to the mixed state. That's the microcanonical ensemble. So in gravity, we believe that the dual theories are chaotic theories. And so for any finite value of n, and if we choose some high energy pure state in the CFT, we may say this is dual to a black hole, but it's really dual to the full spacetime, and there's no sharp horizon yet. So I've kind of pictorially drawn this like this. So even at large n, if we take some high energy pure state on the CFT, this has to be dual to some pure state in the bulk. But as we take n to infinity, a horizon can really emerge in the same way as in ETH, and we can get that this sequence of states converges to a thermal state. So this is the sense where we can have information loss when we just look at simple operators. We only get the thermal state in the exterior of a black hole. So the analog of this UHF algebra in these large n gauge theories is generated by single trace operators. So these are the analog. This is the analog of the Pauli spins, the finite chain of Pauli spins. So we have some single trace operators that populate a Fock space of free particles in the bulk in the large n limit. So Liu and Luthauser very interestingly showed some properties of the algebra of these operators in the large n limit. They form some closed algebra, and this has led to several fascinating advances in quantum gravity, I think. So the thermal field double state has a large n limit as a pure state, and this played a major role for these authors. So this has a large n limit as a pure state for the single trace algebra. And this is dual, as we said before, to either the two entangled ADS spacetimes or the eternal black hole, depending on beta. And so we can ask, what about the PET state with the baby universe? So in conformal field theory, each state can be prepared by inserting a local operator on the north pole of the hemisphere. So here I've chosen some blue operator to be this local operator, and that's the hemisphere. And so the CFT path integral for the expectation value onto, we're going to choose, for simplicity, some projection operators on the left and the right. So here I have a projection operator II on the left and JJ on the right. And I ask what the expectation value in this PET state is, and I call that Mij. And I call the normalization of this PET state N. Pictorially, in the CFT, we have these path integrals. This is a Euclidean partition function, the same one that we would do for the thermal partition function, except we've inserted this heavy operator O. And we've capped this off with these states. And so this represents Mij, and this represents the normalization. And so we're going to compute these using the ADS-CFT correspondence under the assumption that the bulk dual of these states is this baby universe geometry. So we've heard a lot about how the gravitational path integral is computing some sort of average. And I'll comment more on what sort of average this is going to be, but as in other talks, I'll put a bar over my observable when I've computed it using the gravitational path integral. So in order for some expectation value, so this is the normalized expectation value, to converge at large N, the variance must be 0. It shouldn't be oscillating at large N. Otherwise, that's just not a convergent sequence. And so a useful criterion for this sort of a ratio to converge at large N is for the normalized variances of both the numerator and the denominator to be the same, which gives them a chance of canceling. So because we sum over all geometries and topologies in the gravitational path integral, we're going to compute the square of this matrix element and take the bar, meaning we're going to compute the square using gravitational path integral. And so here, I've just drawn the square, so I'm drawing 2 copies of this and filling it in gravity. And we're assuming that it's dominated by the geometry with the baby universe. And so these dashed lines are supposed to resemble the baby universe. And then I have the double lines are connecting this with this, and the green is connecting this with this. And there's 2 contributions to the gravitational path integral. There's when we compute the square, we have the cross correlations too, and this comes with an exactly equal weighting. You can see that there's no difference in these path integrals. If we had only computed the expectation value itself and then squared that answer, we would only get 1 contribution. And so the normalized variance, this value for Mij, is just the number 1. So now that we've computed Mij, or the variance in Mij squared at large N, we can compute the normalized variance of the normalization factor. So the normalization factor just looks like this, while the normalization factor squared also has this cross correlation, as in the previous slide. And you can note that, if you're familiar with computing Renyi entropies, this is the same sort of path integral that you would do to compute the second Renyi entropy of the baby universe in the bulk, of the quantum fields in the baby universe. Equivalently, because it's in a global pure state, tripartite pure state, this is the second Renyi entropy of the 2 ADS regions combined. Now, the Renyi entropy has to be finite. And so the normalized variance, if you compute this, is e to the minus Renyi entropy. And that is some finite number, some finite fluctuation. And so therefore, the state does not converge because the normalized variance is different than, of the normalization factor is different than the normalized variance of Mij. And this is going to hold for the same simple reason for any state with a baby universe. And so this is what resolves the puzzle, is that there's really no semiclassical limit of these states that have baby universes. Okay, I've quickly gotten to some speculations. So we propose that standard ADS-CFT does not allow for a semiclassical description of closed universes because the states do not have large n limits. And what I'm calling standard ADS-CFT is just taking the value that you get at any finite value of n and literally just taking that limit. And if that limit doesn't converge, that's not working to match the gravity solution because the gravity solution is giving some smooth behavior. And so we can ask whether this situation is hopeless, and hopefully you are at Hong's talk, and we don't think it's hopeless, but so we want to keep pushing. And so we just have to do something more. We have to think about some modified version of ADS-CFT that allows for some semiclassical description. So psi-n did not converge itself, but we could consider other sort of limits. In Hong's language, these are different filters, which one could perform some sort of averaging or some sort of filter more generically. And I'm going to consider what it would mean to average over n. N is generically the only parameter we have to play with. And so it would be the most natural thing, or that's arguable, but it's something that you could average over that you have in all of these theories. So let's say that psi-n did not converge, and we did some averaging procedure, like we took an averaged version of psi-n, where we average over n, then the limiting state that you can get will necessarily be a mixed state. So if we take this mixed state that comes from averaging over n, or some other form of filter, then the algebra that we have, the single trace algebra, is going to act reducibly on. We have this state and we have some algebra, so we can build some Hilbert space using the GNS procedure, and the algebra of single trace operators is going to act reducibly on this Hilbert space, which means that there's a non-trivial commutant. A commutant is all of the operators on the Hilbert space that commute with our original algebra. So finding this algebra that has a non-trivial commutant is really something that is only going to be possible in the n goes to infinity limit. And this is where the single trace operators form that closed algebra. And so we'd like to associate this commutant to the operators in the baby universe. So the single trace algebra is going to be dual to operators, for example, in the causal wedge. So in this case, with two ADS regions and the baby universe, the single trace algebra is going to describe the operators in the ADS spaces. So you can ask, what are the operators that purify this mixed state in the ADS spaces? Well, it looks like it's the closed universe. So in the black hole regime, the commutant could be similarly associated with the interior. So we thought a bit about what it would mean to average over n when you have these highly fluctuating, when you have a sequence of numbers that have these erratic behavior. And it seems quite difficult to come up with some smooth large n behavior. I'm just going to write the perturbative series here. So let's say we have, let's say that perturbative quantum gravity gives us some sequence in G Newton, and we want to reproduce that using the CFT. And so in particular, we want to reproduce some asymptotic expansion in n. Theta is some observable, that's a function of n. And we have the term that's independent of n, and then we have all these subleading terms. And so we'd like to be able to reproduce these coefficients A0, A1, etc. So there's a simple procedure for extracting A0, the leading term. There's many ways of doing it, but we could take, for example, just an average over all of the n's. So in this case, even if the theta n did not converge itself, if they're relatively independent, this limit will converge and it will give you some number. It's, however, a lot harder to come up with a way to extract this A1 term. And there's some real obstructions to doing so in the case where you have some sequence of independent random numbers. And so if we just try to do the most naive thing and just solve for A1 and take the limit, the problem is one problem that's going to happen is that this limit is not going to diverge because of the fluctuations that come with summing random coefficients. And it will have, generically, this will have fluctuations at order 1 over root n. And I've multiplied by n here, so this would diverge as root n. And the coefficient of this divergence would be some random number. So it seems hard to even extract the first perturbative correction if you have a sequence of random numbers. So this is speculative. We haven't worked with this so much, but a potential workaround to this problem, or a filter, is so it's very hard if you have a sequence of genuinely random numbers. It doesn't seem possible to extract some asymptotic sequence, some asymptotic expansion. However, if we make another assumption that these theta n, which were originally just defined for integer values of n, if we assume that these were, if these came from actually evaluating some preferred analytic continuation, so theta of n, meaning some actual analytic function of n, if we have that just evaluated at the integers that forms this sequence, so even if this limit did not converge, we can take a Mellin transform, which is taking this analytic function and integrating against n to the s minus 1. And this is going to encode and the analytic properties of this theta s are going to encode this asymptotic expansion. So in particular, we can then just define these coefficients an as the residue of this, as this function, as this Mellin transform at the positive integer values n. And this is suitably analytically continuing this Mellin transform. You can check that this sort of Mellin transform is not going to disturb observables that already had good large n limits. It preserves the asymptotic expansion. And it provides an asymptotic series for some large class of observables that did not already have a limit. For example, if we took something with a large n asymptotic expansion and multiplied some cosine n term or cosine squared n term that's oscillating, so it doesn't have a limit, even so, you can plug it into here and extract just the smooth part and get rid of the erratic part. I don't know right now for what sort of observables this is going to work or if this is the right idea. So if you want to be more ambitious and extract a whole trans series, something that is going to be given to us by gravity, you could consider a bit more complex of a transform, some of both Laplace and Mellin transform, which probably has a name. And now you have two complex variables, s and t. And from the analytic properties of this function of two complex variables, you can now extract some trans series. So this is going to preserve trans series that already had good asymptotic expansions, but it can also get rid of some erratic behavior. I'm not sure exactly what sort of erratic behavior is too bad, but at least for some simple erratic behavior, it will actually get rid of it. Okay, so this is some proposal for a filter, but it's a work in progress. And it certainly might not be the right answer. So I'm going to close with just a fun idea, which is we're proposing that a baby universe might only be well defined in a perturbative expansion around infinity. This is because we're proposing that it's coming from some commutant of this algebra. that only is non-trivial at infinite n. And you could ask, what's the bulk manifestation of this only being a well-defined notion at n equals infinity? And so the baby universe in this AS squared scenario, and perhaps more generally in ADS-CFT, are Big Bang, Big Crunch cosmologies. So they only live for a finite amount of time, even though this can be a somewhat large amount of time, but they only live for some finite amount of time. And so in this sense, they're like unstable particles in ordinary field theory, which are really not precisely defined to exist, except when they're asymptotically long-lived. And so these baby universes maybe are thought of as some sort of resonances in quantum gravity, which you can only precisely make sense of in some 1/n expansion. So I'll leave you with this. Thank you.
My first question is, how much of this apply to, let's say, completely evaporated black hole?
Completely evaporated black hole?
Yeah.
Yeah, so if you have a completely evaporated black hole, and you look at the simple, like the single trace algebra, if we're talking about, say, ADS coupled to some Bath, that is, and we can consider some sequence of states in n, that's going to converge, and that's going to converge to a mixed state. It's going to converge to the thermal state, which is Hawking's answer. Now, as Juan mentioned at an earlier talk, if you take that fully evaporated black hole and evolve for some Euclidean time, that's very long, then you could go back to the scenario where you don't have a large n limit anyway. And these fluctuations are really controlled by the Rényi entropy or the coarse-grained entropy, or the Rényi coarse-grained entropy. So which is infinite after the fully evaporated black hole, but it's finite in this AS squared scenario. So anytime that you have an infinite amount of coarse-grained entropy, you're going to get some convergence to a mixed state. For example, these long wormhole scenarios.
But we still thought that we claim that completely evaporated black hole is pure.
Yeah, it's mixed with respect to these simple operators. The single trace operators don't see that. It's for the same reason that and this is in the semiclassical limit. The same reason that if you drop all these non-perturbative corrections, essentially that Hawking may have dropped, then you get a mixed state, and that's a fine calculation. So it more matches to that because it's simple operators. It's not these very complex operators that can detect whether it's a pure state or not.
How about instead of doing Euclidean evolution, we just do some measurement of the radiation?
You measure it.
Simple measurement.
A simple measurement. This will be protocol dependent.
Maybe I just want to change the regime from this to from the completely evaporated black hole to this.
Yeah, well, yeah. Let's say the black hole has entropy 10 to the 50.
Yeah, then it does not have a large entropy.
Yeah, then it'll be like this. But I feel like a black hole whose entropy is 10 to the 50 should be pretty semi-classical.
I think the first lecture at this conference by Almeri illustrated what you're saying, because he had the black hole completely evaporating to a final state, which was an entangled state of photons with a baby universe. But in reality, there only were photons. So the interpretation of the baby universe might be as in your lecture, that the photons are actually a very complex pure state, but the simple algebra is a commutative, which corresponds to the baby universe. So the very complex pure state has a simpler description in terms of entanglement with the baby universe. That would be an asymptotic statement for large n. I should have better said, for finite n, it would be clear that you only have finitely many photons, and there's no confidence.
There is a particular example of a baby universe in the context of the ADS-CFT correspondence in the strict large n goes to infinity limit, where you consider a charged black hole solution. In the penguins diagram, you have infinite copies to the future and the past. And wouldn't you interpret them as baby universes?
Those each have asymptotic boundaries. Yeah, what I mean by baby universe here is closed universes.
Thank you. Very nice talk. One question I have is, so if I understand well, the fact that this state doesn't have a good larger limit is dependent on the fact that you have an order 1 entanglement, right?
Yeah, crucially it is one entanglement. But that always happens if you can't have diverging entanglement if you have a type 1 algebra. Yeah.
Now, if I take some microcanonical setup in the bulk here, I could imagine a case in which I have an entanglement that does scale with n, possibly not with n squared, maybe with n or square root n.
Usually 18 over 17, which is in your paper.
Yeah, for example. So in that kind of case, would you obtain a good larger limit with a mixed state, and so directly this commutant you could interpret in terms of?
Yeah, in that case, you would have a larger limit as a mixed state, and then maybe it's a good playground. Maybe that sort of part of the phase diagram is a good place to play with these ideas. Yeah.
Yeah, within the context of either averaging or the Mellin transform or something like that, can you comment on how you would want to think about operator reconstruction in the baby universe? So the way that I understand how you get the operators in the commutant is that you do the GNS construction and then you have this commutant. But then how am I supposed to think about the reconstruction at finite n, given we're also averaging over n?
Finite n? Or
just on the boundary in general?
Yeah, I mean at finite n there's no commutant. So, but at infinite n, yeah, I don't know the procedure for. Okay, I said these words that maybe the commutant could be the baby universe, but I don't right now have much more to say than that. I wish I had a better procedure. What Hong said in his talk with, for example, this in the Maldacena mouse wormhole setup seemed promising to me.
I guess maybe one suggestion is very large but finite n. You could imagine purifying the system with some auxiliary system that just records the value of n. So you have some ensemble of n, and then you could compute the entanglement wedge of that auxiliary system. I think according to what you're saying, for very large n, you should expect the entanglement wedge of that to contain the black hole interior or this baby universe. But I think, yeah, well, replica calculation would be a little bit interesting.
There's one, yeah, that'd be interesting. There's one subtlety I just want to say is that when we have finite entanglement entropy at large n, it's much less sharp notion of entanglement wedge. So it's a bit harder to. So for here with baby universes, where it didn't converge is if there was finite entanglement at large n, and without this parameter that's diverging, it's much harder to define these entanglement wedges, but that could be possible.
One comment, yeah. One comment related perhaps to what you were saying is that when you average over n, there are not many things you are averaging over. And so the fluctuations will be quite large. There will be a further square root of n or 1 over square root of n or 1 over n. Now, I don't know that this is a big problem, but for example, in that, what Henry was saying, that the entropy you can store is before the logarithm of n. But while in the closed universe, naively, you may have bigger entities. But now, and I think that is also related to this, is that most of these wormhole calculations, when you consider many wormholes, you tend to get, if you consider the simplest diagrams, you tend to get some distributions which are Gaussian, perfectly Gaussian. And then the non-Gaussian corrections would be extra wormholes connecting the different copies. And so this fact that that the fluctuations are of order 1 over n and so on, would say that perturbatively, the little wormhole should be perturbative couplings. We don't know. I don't know, it's just a comment. Maybe this is the truth. This is what we should expect. But it's slightly unusual. It would mean, like, for example, that in string theory, there are things already at the first order or second order in perturbation theory that we don't know, couplings we don't know.
but this Manin transform will avoid this issue, right?
Well, this is a mathematical discussion. I mean,
Yeah, when you have a continuous variable, then you don't have variable constraints.
So one comment is also the like coefficient that comes with square root of n is a coefficient that I don't think we can determine. Like it's a random coefficient. I guess it's pseudo-random if we actually take a particular sequence. Yeah, I can't rule out the possibility of the small wormholes. Yeah. This is under the assumption of some process. Thank you.
Okay, I think with that, let's.